Hello again, Physics 243. Let's do a couple more examples, this time based on the stuff that we just covered on pipes and strings. Here's one. A standing wave of the third overtone is induced in a 1.2 meter pipe that is open at one end and closed at the other. Speed of sound is 340 meters per second. How many antinodes are there in the standing wave pattern? And what is the frequency of the sound produced? Okay, remember that the third overtone is the fourth mode of oscillation. So the first mode of oscillation is the fundamental, right? That's got the lowest frequency. After that, you have a first overtone, a second overtone, and a third overtone. So that's the one that we're discussing. All right, so how many antinodes are there in the standing wave pattern? Well, draw a picture. I guess there's a formula, but I never remember it. So I just draw a picture. So start out with this, right? This is the pipe. And these lines represent the motion of the molecules, right? Here's a node, has to be there because we have the bottom of the pipe. These air molecules don't move. And at the opening here, they move back and forth. That's what the red and green lines depict. So that's the fundamental mode of oscillation. The next one is the first overtone, and it adds a node right there. Second overtone adds another node, and here's the third overtone. So it's this complicated one down here. Okay, so the problem says how many antinodes are there? So let's focus in on that one. Antinode is the opposite of node. Node is where the particles don't move, and the antinode is where they do move. So here, and here, and here, and here. So there, I have arrows. Here, 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 and here. So there are 4 antinodes and 4 nodes. All right, so the answer to part A is 4 antinodes. For pipes open at one end and closed at the other, remember we have this formula for the frequencies based on the fundamental frequency, F1, which is the speed of sound divided by 4 times the length of the pipe. For the third overtone, we pick M equals 7, right? So fundamental, first overtone, second overtone, third overtone. So M equals 7. That gives us then a frequency of 7 times the fundamental frequency. Now, what if you don't remember this? Well, remember how we got this. It follows from the picture. So the length of the pipe is L, and one wavelength is this. So you could either look at this one, right? That's one wavelength, or this one, that's one wavelength. And now, how do you express lambda in terms of L? Well, this is a little maybe, you have to look carefully, right? So the waves here divide L into sevenths. So 1, 2, 3, 4, 5, 6, 7. If I draw a line there at the node, and a line at the antinode, and a line at the node, antinode, node, antinode, I divide up L into sevenths. And in the space of one wavelength, then I have 4 sevenths. 1, 2, 3, 1, 2, 3, 4. So looking carefully, you see that the wavelength is 4 sevenths of L. And then you plug it into this relationship. So remember that the speed of a wave is lambda times f. In terms of f, it's the speed of the wave divided by lambda. Plug in that wavelength and you get this. Okay, let's plug in the numbers. Speed of sound is given as 340 meters per second, and the length of the pipe is 1.2 meters. So that works out to be this number, which we can round to about 500 hertz. So this mode of oscillation in a pipe is about 500 hertz. And with a big, a big long pipe like this, this is probably an organ. So it's not unreasonable to excite higher modes of oscillation like this. Okay, that's one example. Let's do another. This one is about strings. So a 0.32 meter violin string, so 32 centimeters, is tuned to play A above middle C. So that's 440 hertz. Concert A. What is the wavelength of the fundamental? What is the frequency and the wavelength of the sound wave that is produced? And there's a difference. Why is there a difference? All right, so A, what is the wavelength of the fundamental? So remember this picture for the oscillations for the standing waves on strings, right? And this is what the string looks like at one moment. The next moment it's flat. Next moment it's down here. Next moment is flat, and then it returns to that. So what we see here is half a wavelength. Right? So lambda is 2L. L is the distance from here to here. We don't have that labeled. And so we can plug in the number because we were given 32 meters for the length, or 32 centimeters, excuse me. So the wavelength is 64 centimeters, or 0.64 meters. That's the wavelength of the standing wave on the string, the fundamental mode of oscillation. All right, so what is the frequency and the wavelength of the sound wave produced? All right, so the sound wave that is produced has the same frequency. Frequency is 440 hertz, right? Because the way the string is moving back and forth 440 times per second, so it's pushing the air 444 times per second, and so the frequency of the sound wave has that same number of pulses per second. The sound wave that is produced has the same frequency as the string, 440 hertz. But what is the speed, what is the wavelength of the sound wave? So we use this formula here, except we use the speed of sound, 343 meters per second, which was given in the previous problem. And we get 0.78 meters for the wavelength. So that wavelength is different from this wavelength. Right? That's the wavelength of the sound that is produced, sound wave that is produced. This is the wavelength of the oscillation on the string. And the difference, they are different because the wave speeds are different. The speed on the string is some value, and the speed in the air is something else. Right? So even though the frequencies match because the string pushes the air, the wavelengths do not, because this relationship and the speeds v are different. V on the string is different from V in the air. Okay. All right, so I just wanted to do those two. Next up, we'll talk about two-dimensional modes of oscillation. See you then.